As people are finishing up and finishing the poll questions, David, if you'd like to go ahead and get into the presentation, I think we're ready.
Very good. Thank you, Michael. Appreciate it. So I'll give a couple of slides on the corporate presentation, and then we'll get right into the product for the additive manufacturing. So you can see a couple of the customers listed here. In North America, we're pretty proud of our data translation, which is the core of our company. And companies like Lockheed Martin and Fiat that had the largest migration worked with CoreTechnologie on that, just to name a couple of the customers. So a little bit about our products. Today we're focusing on the one on the right-hand side, which is the 4D additive, but I'd like to start off on the left side and talk to you a little bit about our product 3D Kernel IO. If you're not using any of our solutions today, you may be using it through some computer-aided engineering or computer-aided design or manufacturing software companies that have embedded our software development kit. So every time you use those technologies, you hit file open and you're opening CoreTechnologie's libraries. Those libraries are unique in the fact that they provide both a boundary representation, which is a solid model like a step file, or more importantly, the full parametrics of a model. And we've incorporated those libraries into our products, 3D Evolution, 3D Analyzer, and 4D Additive. The 3D Evolution software has been embedded in over 400 customers worldwide. In some cases, they're embedded into the PLM systems. So although the users of the companies are unaware that through the background, we may be running a translation, or more importantly, reducing file size of a computer-aided design file based on the requirements of that organization, from a plant layout, use case to file size reduction for protecting IP, and then also for packaging as well. And then we have our visualization software that doesn't require a translation at all. You just hit file open and you can read in those file formats and interrogate it for costing, interrogate it for revision controls or collision detections, or more importantly, the wall thickness or backlash detector. And today we'll focus on the additive manufacturing software. So the CAD native interfaces that are read in all of our products are, again, repeating a little bit, but are without the necessity for reading in the APIs from the CAD systems. And then more specifically on the additive manufacturing interfaces, I just kind of wanted to point out the tessellated formats. So unique to CoreTechnologie is our additive manufacturing software, 4D Additive, allows you to open up both a BREP as well as a feature-based, which a BREP as well as the tessellated model, which Laurent will show you in the demonstration today. What you will not see today is our product part finder. A lot of times on the additive manufacturing, there's different parts that are already made available in databases. So folks want to go out and just research within their own database before recreating a part, the volume, the specific bounding box calculations, or the bounding box of the parts of an assembly, or inertias, volumes, areas, masses. And you can go through and do a calculation for that. You can even look in the technology for the fully featured model. You can see on the screen the actual parametrics that were created. This looks like it might even be a NX file that was used here. So just like you're using NX or Creo or CATIA, when you're opening up the full parametrics, you can look and research those file formats based on number of drafts or holes or diameters on the part finder. It's interesting, this part finder was actually set up originally when we started doing the migration from one CAD systems to another, so we weren't duplicating when we were translating parts. And then we were able to use the same technology in our part finder. You can actually dive down into the metadata and pull out the attributes of the file as well. And then once you've gone through the filtering, once you've found the database, you can actually go and take it one step further and then even filter for specific entities within the model related to the classification or other information, like if you see thickness of an average ray on a particular part and then honed down. The nice thing about the technology is once you've gone through your analysis or your research point, you'll get a result that looks something like this. And the nice advantage of it is you get a picture of the actual part itself, the results of where the CAD system was, and you can change these particular criteria here. But the big advantage is once you've set that up in this SQL database, you can actually drag and drop the actual part into a visualization tool or a 4D additive tool to see if that's the part that you want, and then interrogate it even further without having to go through multiple file sets. So this is part of complement of some technologies that are used in the industry. Folks are looking for part solutions. As you can see, this is the result of pulling that data set from a visualization standpoint, and you're pulling it up in a 3D model. So it's not just, you know, a TIFF image giving you the data set. And so a little bit about the process that you're going to see today that CoreTechnologie has aided HP and other companies to implement our software as a complement. So Laurent, I'm going to let you take this slide and talk a little bit about your process that you've used as a product manager of the additive manufacturing.
Okay. Hi everybody, this is Laurent. What I try to explain to you is that I broke down the workflow to basic steps, like just 3 steps. So you start in the 3D CAD environment where the design actually happens of the parts. Then what we have to do is we take the 3D model, have to pre-process it for the AM software for the preparation of the 3D print. And at the end of the process, it has to be sent to the 3D printer and is then manufactured. So in the design area, there is either the way of directly designing a part that is made for 3D printing, so with a special AM design, or what is also happening at the moment is that companies take parts that have been conventionally manufactured and try to print the parts, the part as it is. So you see already here in this area is like a question that comes up. So which parts that are conventionally designed can be used for 3D printing? Then what is happening in the AM software sector is the pre-processing, like quality check, positioning of the parts, optimization of the machine, and then in the last step is the AM process. So the first product that David talked about is the 3D Part Finder. So it tackles actually this identification problem of we have a big database of conventionally designed parts, and we want to know where are the use cases for 3D printing. And this is where 3D Part Finder comes in to filter the big database and to find use cases that can be really good for 3D printing. And the second one, which we are going to show you today, is 4D Additive, which is located in the pre-processing. And what is actually the big advantage of our products is that we are using the exact BREP geometry. So there is no transition between the design, the 3D CAD environment and the AM software environment, because we can directly use these native CAD files and pre-process them for the actual 3D printing process. And that's what makes a really consistent workflow throughout the whole process.
Yeah, just to add to that, thank you, Laurent. Just to add to that, and when we talk about that exact BREP geometry, when you get to a certain point in the process, which you'll see him show you in a live demonstration, you change from a boundary representation to an STL. And this is the key advantage of using our technology over other technologies that are available out in the industry. A lot of companies are stepping up to the plate to create an additive manufacturing software for both pre-process as well as post-process. So continuous, again, is kind of what I mentioned. Unique to CoreTechnologie also, compared to some of the other technologies, is if you have some consistent printing processes based on the nesting and slicings that will be showed, you can actually batch process that technology as well. And this was incorporated in a requirement for a small, if you will, cookie cutter company that was printing tons of cookie cutters and needed to batch process because they had 8 different printers out on their manufacturing floor. And so, and we talked a little bit about this already. I'm going to skip through that. So the powerful analysis tool, at the end of the day, part of the reason why you're bringing in a boundary representation is because you want to have less post-processing, right? After that part is printed, you want to be able to do an inspection on the part, it's completed, and it's gone off to wherever that part goes after it's manufacturing. So we've taken our technology that we had in some of our software 3D evolution many years ago, which was, let's take it one step further and let's make sure that the model is correct before we print it. Let's check the quality of the model and be able to clean it. Let's look at the surface areas and analyze that surface area for specific massive zones or wall thickness or thickness checker or collision detection, which I think I have in the other part. But my point is that you get to the point where you want to analyze the data very quickly so that you can pre-process the data. Even more importantly, understand not only the collisions, if there are any, and being able to make the changes to that in direct modeling solution of our software, but also look at draft and undercuts, which we'll show in our presentation. So I'm not going to spend too much time here. One of the other processes is not only the direct modeling that was mentioned in the previous slide, but for hollow and lasix structures, this is a key also competitive advantage that CoreTechnologie has. It's something that's required in the industry, and this helps support your printing process to be able to reduce the actual material that's used. And then lastly is to be able to add texturing. This has been requested from many companies around the globe for individual parts or smaller volumes of production and being able to add their own texture. It's very unique in the additive manufacturing, certainly adds in the value to be able to produce one product or produce 1,000 products. Companies have spent hundreds of thousands of dollars doing it. Now they're finding the challenges of being able to print properly and not having to have waste in their process. So in addition, CoreTechnologie, which you'll see today in his demonstration, also supports both from a metal standpoint as well as a plastic standpoint for structuring, for adding structures and attaching and slicing as well. So you can see the process of which it's built, and then the nesting, depending on the size of and the parts that you want to try to print at one time, which you'll see. And so just to reiterate Laurent's presentation earlier, we talk about the 4D part finder, which you won't say today, and we'll focus today on the additive manufacturing. I'm going to stop showing my screen and we're going to pass it over to Laurent to get right into a live demo.
Okay, so I'm going to share my screen. I hope everybody sees my screen. Maybe David, you can confirm.
Confirmed.
Okay. Great. So yeah, what you see now is the graphical user interface of 4D Additive. The first step when we open the software will be to select the type of machine you want to work on. So we have a machine and database where you can select your machine, also filter by a manufacturer, different technology, or also the material family, depending on which material you want to use. And you can then set up your machine. Also, you have a lot of different parameters. I won't go too much into detail. So you can really customize your own machine setup. So I'm just going to use an HP machine for this demo because we have one in-house. And I'm going to open a model. So in this case, it's a CATIA model, like you've already heard from David. So we can open all sorts of different CAD files. It's more than 24 native CAD formats. So you are really flexible in this case to use the BREP geometry, and I'm going to show you the advantages of that. So the software is organized in different modules. So you see here this workshop bar at the top. So it's organized in different workshops, and these follow the actual workflow. So what we would do is we would start with the healing. So then making sure that the model is watertight, so that there are not any holes inside the model that could cause problems in the 3D printing process. And here at the right side, we see the functions according to the actual workshop. So it's really intuitive, and we try to keep it really simple so that the user can focus on each step of the workflow. I won't show you too much into detail how we repair the parts actually, but the algorithms we use are certified by the German automotive industry. So we have checking profile that is according to the engineering standards. So really high standards to make sure that we have the best quality possible. Okay, on the left side, we see the typical machine properties of the machine we just chose, also material properties, and all the properties of the actual machine that we are going to prepare for the print. So the next step would then be to analyze the model after we made sure that the model is has no geometrical errors. It is then important to make sure that the part has been designed in a way that we can use it for the technology we want the parts to be printed. So the first really important check is the wall thickness check. I'm going to show you the result. So what we see is highlighted in different colors, the different wall thicknesses. We can just click on the model and see how thick the part is in this specific area. Maybe I will make it a bit transparent so that we see better the different areas, and then we can analyze. We can also filter if you want to see only a certain wall thickness to be sure to have a better overview where the critical areas are, and then the user can see if the part has been correctly designed for the printer and the technology he wants to use, or if there are any adaptations that have to be made. Okay, this is one really important one is the wall thickness check. I'm going to show you second analysis tool, which is really interesting also for powder bed fusion technologies, because these technologies have the specificity that we have a lot of different parts in the machine, and what can really cause problems is really dense parts where we have a lot of material that has to be fused together by a laser or another energy source. And in this case, you see here we analyze the areas where we have a lot of material density. So we can, it's the same principle. We can just click on the surface and see the distance from the center of this massive zone, we call it, to the outer surface of the part. And this is then really interesting to see if there can be any temperature problems, any heat zones in the machine later. So this is, for example, then for this part, this would be an area we have to change the part. And in this case, we would hollow it. I'm going to show you that because we have also integrated a hollowing function. And what we can then do is either hollow the part and leave the inside empty, just define the thickness. In this case, I would say 4 millimeters, but we can also add lattice structures inside the part to make sure that we won't reduce the stiffness of the part in the actual 3D printing process. So we have different kinds of lattice structures we can apply here. I will choose the honeycomb structure, and I will show you the result in a few seconds. Okay. So I will do a section cut through the part, and then you see here the actual honeycomb structure we just created. Yeah, this is really quick to reduce material consumption, and of course also to tackle these temperature problems that can occur when we have these big massive zones, a lot of material that has to be fused together. And the really unique thing about 4D additive is that now, if I change to, because what you just see here is like a tessellated representation of the part. So you see here all these little triangles. So what we did is we created the hollow and the lattice structures on a tessellation of what was at the beginning a BREP part, a BREP representation. But I can switch back to this BREP, which is a really lightweight model because it just has a certain number of faces. And what we can do is we store these two different kinds of information. So the original representation of the part, which is the exact representation which comes directly from the CAD system. And we have tessellated representations where we can store complex information like hollowing structures, lattice structures, and later I will show you the texturing module, which is also based on the tessellation. So we store these different kinds of information in these two layers, and we can switch between these two layers at every part in the software. And you see here, for example, we now store these honeycomb structure in the tessellated representation, but we can then switch back to the BREP and continue our positioning, the orientation of the part. And it's still then a really lightweight model, but which carries these information inside, which can be really complex. So we have a big advantage here that we can store it in another representation and continue to work on this part, and we don't lack in performance when doing other stuff.
Laurent, this is really cool that you could switch so easily from that. We do have a question that's related to this from Marianne.
Yep.
Can you change the scale of the actual part pretty easily as well?
Yes, of course. I can show you that in the actual placement and positioning of the parts. So we have a scale function here with predefined scales, but we can also apply a certain scale. Yeah, that's no
Very
problem.
good, thank you. That was a good question.
Okay, so what I showed you was the wall thickness check and the massive zone detection. What we can also apply is that based on these analysis, if we want to adapt the model, we can also change the model with our direct modeling functions. So what we can do, for example, is we can apply an offset. So if we have, for example, here this phase, we know this is going to be milled afterwards, for example, if this is a metal part. So we can just select the exact faces and then apply, for example, 0.5 millimeters. And this is where we just offset this face pretty easily. What we can also do is we can, with this offset, we can change the diameter of a hole, for example. We can select a positive offset or even negative to make a bigger hole out of it. So you see, I can really adapt. I would just quickly change my rendering so that it looks a bit smoother. Yeah, so I can just adapt the size of a hole, for example, pretty easily. We can also use our direct modeling tools. So I select the faces of this cylinder. Then I see here displayed, for example, the radius, and I just change the value of the radius, and it is directly applied. I can also select a phase and just drag it to create an offset. Yeah. So this inside 4D Additive, you also have strong modeling tools to adapt the parts to your needs. I will also show you the defeaturing function. So what we can do is we can also delete fillets, for example, if you want to apply a different radius, for example, or you want certain details you don't need for 3D printing because maybe it was a conventionally designed part and you want to change some details. I hope this works now because maybe in the background. Okay. Just quickly restart.
Okay, it shows that you're actually using the software. It's not a PowerPoint we're running through.
Yeah,
Movie
maybe
through.
because I
Right.
changed the, yeah,
Yeah,
I
that's okay.
changed the, because
Yeah,
I did an analysis and maybe in the
sure.
background it caused a
Yeah.
bit of troubles, but you see I can just delete the fillets here in this area and make it more simple because I don't need, for example, all these fillets for 3D printing. Or what I can do also is I can apply a new fillet, yeah, to my part. So you have really tools to change the geometry of the part according to the 3D printing process. Okay, so after we checked all the errors on the part, we repaired it, we made the analysis, some modifications on the part. Then a really important step is to find the right orientation. So I will show you. We have strong analysis tools to find the best way how to orientate the part inside the machine. So what we analyze is actually the surface quality, so the roughness of the part. It can either be support roughness, which is related to the angle of the maximum angle of support. So what this analysis does is it analyzes which faces need support for the specific technology, and then you will see which phases are affected by support, and also which phases have to host support. So I will just turn this around, and you see here all the red phases are the phases which require support, and then we can, in real time, we can just change the orientation, and then we see how the phases change actually. Yeah. So,
Hey, Laurent, we
yep.
have a question. Sorry to interrupt.
Yeah, no
so
problem.
we have a question. How do you make sure of the design's strength when you apply the hollow feature to the model?
The hollow feature is really a way to reduce material consumption, and to reduce these massive zones. What we don't do is we don't simulate any forces that are applied on the part. So we have not simulation integration, if this is the question is aiming to. So we can't make sure that the part will afterwards have the same properties than it had before. But it is really useful also in the prototyping sector to quickly reduce the material consumption.
Yeah, that was good. That was actually a good question. So the idea is when you're building your structures, you can analyze even further after those structures are in the system to see if there's still additional weaknesses in it, but and rerun your analysis if you'd like as well.
Yep.
The structures are built based on those weaknesses of that wall, but that was a great question. We appreciate that.
Okay. Another really interesting analysis, surface analysis, is the geometric roughness. So it's actually based on the layer height, so the stair-stepping effect that occurs with additive manufacturing. So we see here in red displayed the faces that are really positioned in a flat way, so that we have big stair-stepping effect on these in this surface area. And if we now change the angle of the part, we see how the surface quality changes. So this is another really interesting analysis based on this stair-stepping effect to help the user find a good orientation of the part. And the third one we have is a analysis based from experimentation. So we collected data from experimentations from universities to have actually the real ratio of the roughness based on the angle, and you can also apply that for the specific technology you want to use. Okay, the next step would be support structures, depending on the technology you use. The technologies that require supports like metal printing, SLM, or stereolithography, SLA. So I'm going to show, I won't go too much into detail in this specific area because I want to show you also the great 3D nesting features we have for the placement of the parts, and also the texturing module at the end. So I will position this part in good orientation. And then we have different kinds of support structures. So simple shape, for example, is like just simple pins We have different shape types, cone, cross, cylinder. Um, you can set up different parameters for that. I will just try one, maybe the cross one. Okay, we can then also select if you want to have teeth, for example, to be able to take the support structures away after the printing for a better post-processing. Okay, so this is just an example. I chose quite big support structures in this case. So we have different shapes, like I told you. Simple shape support is like these single pins. We also have a structured support, which is really interesting for metal, which is needed at the outer surface of the part, the contours. We also have tree support, which is needed for SLA, for example, but can also be used for metal printing. Okay, and we also have an analysis for support accessibility to make sure that the support can be removed in the post-processing. So the next workshop, which I'm going to show you, is the nesting.
Before we get into that, Laurent, yeah.
Sorry, just a quick question regarding the hollowing. After you export the new CAD model and incorporating the hollow feature for FEA analysis. So the question's coming from, so I'm going to make the assumption that you want to take that model that you have, which is the BREP model, not the STL or the tessellated model, and run that through an FEA analysis. So the support structures and the hollowing wouldn't be included in that CAE analysis, so you would still end up with your original model. You might end up with something very similar to the resulted data set that Laurent did when he checked the model to see that there was weakness in the specific wall.
Yeah, so we export the support structures. Yeah, they can be included in an analysis.
Oh, you can.
That is not a problem. With the hollowing and lattice structures, like I said, they are integrated in the tessellated layer. So we would have to export then the original geometry, but in a tessellated format. So we can't, if we just export the original representation, the hollowing and the lattice structures will not be in this model. So we would then have to work with a tessellated.
Yeah, and just to add, to that, when you're dealing with that mixed geometry, a lot of formats support it, and a lot of formats do not support mixed geometry. So we could write out as an example the step 242 format, which is another whole subject, or the JT XT that it will include both geometry as well as the mesh, and then run it if you want to really get into interrogation of the model from a CAE analysis. Good question. Go ahead, Laura.
Okay, so the next workshop I want to show you is our nesting functions, or also the positioning of the parts. So I'm just going to show you some basic how we can actually rotate the part. What is really interesting is when you want to make a first positioning of the part really quick. This works really well with the BREP geometries. Like, you can select the face of the model and then position it according to the different walls of the build volume. So I can select the different walls, and the software will automatically position this face I just selected parallel to this wall. So this is a really quick way to find the first orientation of the part. Okay, so let's assume I have found the my printing position. I will just leave the parts as they are. So I'm going to duplicate the parts. I can just here drag these arrows to duplicate the part. We can also type in how often we need them. So okay, this maybe we can rotate 90 degree and duplicate it. Okay, and this little one we need it, for example. Okay, so I just duplicated all my parts. And now what I will set up is the nesting algorithm. So we can, of course, I will show the nesting in 3D, but it also works in 2D actually for metal printing, for example. Just fill up the whole platform, not going up into Z height. So I would choose 3D nesting. Then where to start, for example, in the middle of the machine. Then you can set up which kind of rotations are allowed for the parts. Actually, the version I'm currently showing you is not the newest release, because we will release a new version in June. And there we will be able to not only set up global parameters, but to set up parameters for each part, so that we can really define the kind of rotations, the distances between the parts, but for each part individually. So if there is, for example, a really dense part where we need bigger distances to the other parts, then we can set up for each part individually. Okay, so I will allow Z rotation with the number of rotations actually can be translated into angles. So for example, 4 rotations will be 90-degree rotations, minimum distance 4 millimeters. And we can then set up other parameters like maximum height if we don't want to fill up the whole machine. But I'm just going to start the algorithm now, and you will see. So we have to voxelize the models, and then it starts pretty straightforward, and we fill up the whole machines first with the bigger parts, and then fill up the rest of the machine with the smaller parts to get to a really high packing density.
Very nice. So Laurent, just to refresh, so I'm giving you a 10-minute warning on this, on the timing left. But keep in mind when he's doing this nesting, it's the reason why it's working so fast, because this is live, it's working on the tessellated data or the STL file outputs that we talked about earlier. It's very quick.
Yeah, and what is included is automatic collision detection. There is a collision detection also if the nesting has been made manually, so that we can check it at the end. If there are no collisions, we can also build small cages, which are really useful for powder bed fusion technologies. For small parts, put them inside a cage, so that is really good for post-processing afterwards for the sandblasting. Yeah, so I want, because 10 minutes you said, David.
Yeah.
I will now go to the texturing module, which is a really unique tool, because we can actually use the BREP faces to select for creating our textures. So what we do here is first we have to select the faces where we want to apply textures. So we can just select them one by one, or select one of them and select all the tangent faces that are connected to the face, to select more faces at once. Then we create the texturing zone. So we see this dashboard to have a preview of how the projection went on the part. We have also another kind of projection, which is called ribbon mapping. This is really useful for complex freeform faces or cylindrical faces, where we have to project the texture in a different way to have a good result. And then the next step is to choose a texture out of a texture database. And in this case, we are cooperating with Substance, which is a really great tool for 3D textures, actually in the gaming sector. And we have included their library. I'm just going to show you if I click here on download. I hope you see that. Just to give you a quick overview, they have over 5,000 different textures with different materials. For example, if I go into the metal section, there are a lot of textures, and this is really great to be able to use them all inside 4D Additive. So I'm going to choose a leather texture. And what is really interesting is that these are parametric. So I can change a lot of parameters. I can, for example, change the resolution. You will see that now the leather gets really accurate. I can, for example, choose if I want to have a double stitch or just a single stitch. I can change the width, the length of the stitch. So everything is parametric. This is really great for individualization. So now I applied the texture. It's just a rendered image on the part. And now I can rotate it, I can scale it, and change the position on the part. Yeah, and as soon as the positioning is good, I then recreate the printing tessellation. So now what you see here is the tessellated part, but the original one. And what we then do is we regenerate the tessellation based on the texture we just applied. And we translate this texture in the tessellation. And what we will also release in the new version is the ability to implement the colors. So what you've seen before is like a red leather with a black stitch, and this will be possible also to translate it into colors and actually export it in a 3MF file, for example, that supports colors, to be able to print the colors also. Yeah, so basically that's it. You just one small thing is that you you can either use the Substance textures, or you can also use your own custom textures, and for example apply logo or a text, for example, or here, for example, I have a pattern of a texture that I got somewhere. So it's just an image file, actually, PNG or JPEG. And we can also apply these as a pattern and translate them into a 3D structure.
This is very good.
Yeah. So actually, that was it.